Hi guys, welcome back to my channel. So today we're going to do an example showing how to use the integral test to show whether a series is convergent or divergent. So let's take a look at the series. We're going to be determining whether the following series converges, and our series is ranging from 2 to infinity, 1 over k, and then ln k quantities squared. So before we jump into actually conducting the series test, we have to verify that we're allowed to conduct the series test. So before we apply the integral test, we need to make sure that we can actually draw conclusions about this series. It has to satisfy the criteria. So the criteria that we're looking for is whether the function is positive, continuous, and it needs to be continuous on 2 to infinity because that is the interval that we're looking at for this series, and decreasing. Okay, so we can do a lot of this with a graph, and that is a little bit less rigorous. That just is very much a style preference in terms of if you're doing this for a class or to try and convince someone of something. Different people require different levels of detail in terms of the explanation. So using technology to graph would be the less rigorous way of convincing someone, and the more formal way of convincing someone is the most rigorous way. I'll show you guys the most rigorous way first, and then we'll look at the less rigorous way to go about it, and you can ask your teacher if they're evaluating you what all they need to see in terms of this. So when we are looking at whether the function is positive, the function that we're looking at is f of x equals 1 over x ln x squared, and we need to know, is it positive on 2 to infinity? Okay, f of x is going to be greater than 0 because x, the bottom factor in the denominator, is greater than 0 on 2 to infinity, and ln x squared, because it's squared, is always going to be greater than 0 on 2 to infinity. Okay, and the numerator is a constant 1, so obviously if we have a positive number in the numerator and a positive number in the denominator, then the ratio will be positive. Okay, so we've explained that it's positive. So when we check for continuity, what are we looking at? We need to see that we won't have any sort of issue for this particular function. It is a ratio, so what we need to verify is that the denominator will be non-zero. So on 2 to infinity, x ln x, does that equal 0? So this can only happen, sorry, it's actually ln x squared. This can only happen if x equals 0 or ln x equals 0, which only happens at x equals 1. So on 2 to infinity, which don't include 0 or 1, f of x is continuous. So if this function were something else, like say an even root function, our check would be a little bit different. We'd be verifying that the numbers inside the radical are positive. So this is going to take you back to your pre-calc work when we looked at finding the domain for a function. That was essentially finding and discarding discontinuity. So it'll be a little bit of a flashback to that. Okay, so we verified that it's continuous. Let's take a look at decreasing, which is probably the hardest one to show rigorously. So if we wanted to show that a function was decreasing, the rigorous way to do that is to demonstrate that its rate of change is negative. So a negative rate of change is represented by the derivative being negative. To save us a little bit of time, I went ahead and calculated the derivative as I would do it. If you want to go ahead and pause it and really take a look at the product rule here, that's what was applied. So we end up rewriting it as a product of x to the negative 1 and ln x to the negative 2. We take the derivative of the first, and then our second term left alone, add that to derivative of the second term, remembering there's a chain rule in there, and producting that with the first term. And then we get a difference of two fractions. Noticing that the denominator is not the same, we would adjust the denominator so that it is the same. And then when we rewrite this as one ratio, the reason we would want to do this is because we want to verify, we want to check. Like we need to actually explain to someone that we know that what we got is less than 0. So here's how I would go about doing this. I would probably try to look at the numerator and denominator separately because I can tell that if I factor out a -1 from the numerator, I get something that I can tell is going to be positive. And again, remember that we're looking at a specific interval. We're looking at 2 to infinity. So I'm not going to think about what happens plugging in fractions for the ln because I'm on 2 to infinity. So because of the fact that x values are only coming from there, I can tell that ln x plus 2 is positive and x squared ln x cubed is also positive. So the ratio -1 times ln x plus 2 times x squared ln x cubed would be less than 0 because you have a negative number times a positive number. Let's take a look at a not rigorous way of showing that this function satisfies the criteria. For a calculus class, and depending on the preferences of your instructor, they might be perfectly okay with you using some technology to assist. So the reason that this would not be considered rigorous is because your graphing technology is never really showing you the full picture of the function. Whenever you look at the window, you always have to wonder what's going to happen outside the window. And no matter how far out you zoom, you're still technically not really ever seeing the whole picture, right? So that's the reason why utilizing a sketch and technology isn't considered actually rigorous. But for a calculus class, it just depends on the instructor as to what their preference is. So let's take a look at the sketch of this graph. Moving to our graphing technology, we want to make sure to have the parentheses around the numerator and denominator so that the technology understands those terms and doesn't make an error with its order of operations. So when we take a look at the graph, we get you can see there's an asymptote happening at 1. The curve approaches that way, and then it approaches the x-axis. So there's an asymptote at y equals 0. So I can tell that this is positive. Okay. And again, I apologize if this seems a little bit elementary, but I've definitely had some students that don't fully realize this. But if you graph your function and you notice that it is above the x-axis, that means it's positive. Okay, so we can tell from the sketch we're always above the x-axis. Is it continuous on 2 to infinity? Yes, it is. Okay, and again, when we're talking about continuity, I'm using my knowledge of the function formula to help me here. So I know there's no asymptotes and holes because, as we saw already, the denominator was non-zero on 2 to infinity. So the picture definitely doesn't show a hole or an asymptote either, except for x equals 1, which is outside of our window. However, graphing technology on a calculator does not show holes, and it's actually pretty bad about making it obvious to a viewer that there is a hole. So that actually is something where graphing technology just does not do a good job for a lot of the more basic calculators that we have. Some of the fancier calculators, I'm sure, can tell you that there would be a hole or an asymptote. But the basic TI-84s that a lot of people seem to still be using, those just don't do a very good job at this. So I'm also kind of using knowledge of formula to verify that. Okay, so positive, continuous, and decreasing. Okay, so when we look at the function, this one's pretty easy to see that it's decreasing. We are approaching the asymptote here. It's going down. It's getting close to 0. Okay, so intuitively, we verified all of our criteria for us on this graph with just looking at our function f of x equals 1 over x ln x squared. Okay, so that's the long story as to all the ways that we could check criteria. And again, I recommend that you check in with your instructor as to what all they want to see from you on this. Okay, so let's take a look at actually applying the integral test now. So now that we've verified the conditions, we can apply the integral test. So the integral test says we can compute the integral 2 to infinity, because that was the value for the series terms. So we're going to be taking the limit as b goes to infinity from 2 to b, and our function is 1 over x ln x squared dx. Now for integrating this, I can see that I have a pretty obvious u substitution. My u is ln x, my du is 1 over x dx. So I can rewrite this integral as 2 to b u to the negative 2 du. And just being careful that if we're going to do a u substitution, we also have to change our limits. So not to get too hasty, we'd be going from ln 2 to ln b. So the limit's only going to apply to the first term. And as b goes to infinity, ln of b goes to infinity, so that first fraction is going to approach 0. And we're just left with the constant ln 2 to the negative 1 for our limit. And then we check in with our criteria. So ln 2 to the negative 1 is also equal to the fraction 1 over ln 2, which is positive and finite. So by the integral test, our series converges. Okay, so before we wrap up the video, I just want to take another look through our whole problem here. And just to reiterate, we do not have to do all of this work and then look at the graph, right? So this is the most careful, the first solution for the criteria that we did was the most careful, most rigorous method for showing that something is positive, continuous, and decreasing. So this is what kind of proof would be required to 100% without a doubt demonstrate these facts. So what we did after that, looking at the graph, that's kind of like, you know, a shortcut that's sometimes good enough for like a calculus class. It's not really a full proof, honestly. So just looking at a picture and not ever seeing the whole story, this isn't really considered a proof. So you wouldn't need to do both of these things, but just know that if you're gonna use this picture, it's a little bit more wishy-washy, and that's the kind of thing where you wouldn't want to do that unless your teacher was like, you know what, I'm okay, I understand that you guys know this and it's pretty elementary, and I'm okay with you writing that. And then here's the part where we actually applied the test. So when you're proving something to someone using one of these series tests, you want to make sure that you, one, satisfy the criteria first, and then you apply the test, and then the third part of your argument for a proof should be a sentence that explains your conclusion. So what you don't want to do for a proof is you don't want to just leave me with 1 over ln 2. I don't really know what that means, right? I mean, you got a number for an integral, but how does that relate to the series? So you need to explain to me your conclusion. This is almost as close to writing an essay as math is going to get. When you prove something, there is going to be language involved. It is going to be an explanation. And sometimes proving something feels so elementary, and people just kind of get in the habit of going like, oh, well, obviously, naturally. And once math gets advanced enough, you'll find people saying obviously, and it's like actually not true, the thing that they're asserting. So sometimes people will use their intuition and they'll be so confident that something goes a certain way, but if they don't check the basics, the things that they're kind of taking for granted as elementary, then that's how things become falsely believed. So whenever a new result in mathematics is posed, people have to bring a full, rigorous proof to someone. You would never see a picture, you would never see that picture submitted to a professional math article. It would be 100% caught by the person editing. They'd say, hey, you didn't prove this to me. You just threw a quick sketch down. You didn't convince me without a shadow of a doubt. And that's the kind of mindset that we're just starting to get into in calculus. We're not really doing anything super formal yet. This is just our first introduction. So those of you guys that are math majors, you're going to get introduced to this continuously. Those of you guys that are engineering majors, you're probably not going to be proving a whole bunch of math results, but you might be proving things if you are someone that's kind of in development mindset, like with your job. It depends on what path you're going. If you're someone that's just kind of repeating algorithms that have already been proven, then you don't need to worry about this kind of stuff. But if you're trying to convince someone that this thing you came up with, this brand new idea is going to work, you have to be thinking with this super careful, very meticulous mindset. So that is something that I hope that everyone can get out of this explanation of how we can do an integral test. Hopefully this helped you guys. See you next time.